been working on Red Hat like 40 years. And in general, I'm working on the X server. And a year ago, I was working on Aiglx, which is what I'll be talking about today. So the first part of this talk is about what Aiglx is, how it works, and some of the problems we had when we tried to do this. The second half of this talk will be about what kind of problems are still in there, what doesn't work, and what's needed to finish this work. So it's sort of a step back from Aiglx and more looking at the positive desktops such as companies and kind of amazing features we still have.
What is it for?
So, yeah, this is not using Keith's new render output mode setting magic. This is the old biggest mode setting driver.
Oh well.
Doesn't work.
I don't know if you can see. Yeah, I think I'll fix it and try to use it. Well, oh, it's I bring you pictures of my
So the normal mode of operation for the X server is that you have a client that links to the X11, and when the client decides he wants to build a rectangle and render a triangle or something, it calls into this X11, puts these render requests into a network packet and sends it off to the X server. The X server then sits on the other side of this network connection and receives the packet containing these render requests, and then takes out the render request and performs them as they come in. So it's the rectangle and wants the triangle and the client request. So and this is a network transparency that X has always had, and this is what allows it to work over a network, and you can have like a remote display over here, and you have the client here, and they will send the render request back and forth. So with OpenGL, OpenGL is of course the 3D graphics API that's available on a number of platforms. And if you want to use OpenGL under the X server, you have to use GLX. And this is a set of OpenGL extensions that specify how OpenGL interacts with the X server and the X environment. And in this case, GLX has two basic modes of operation. There's the indirect mode of operation, which is pretty much how X normally works, and there's a direct mode. So in this case, there's the application who wants to do rendering still links to libgl, which is similar to what libx is when you render regular X requests. So it links to this OpenGL library, which in indirect modes, which is how the X server normally works. In indirect mode, the library will perform pretty much the same task as with X11. That is, if you want to render this 3D volume, you send off the 3D triangles and you send it the textures and give passage to libgl. libgl will then take these rendering requests and put them into a network packet and send them to the X server. And again, the X server is on the other side, so request and passing and renders these commands. The way it used to work was that in this indirect case where the X server receives the rendering request over the network, the X server would have a software implementation of the OpenGL API. So if you wanted to render a triangle, it would go into software that would do scanline conversion of the triangle, perform the texture lookups, and render the triangle step by step. This would all be done in software, and eventually the OpenGL implementation would copy this onto the screen. And that's, of course, way slower than if you have hardware acceleration. So for a while, indirect rendering was slow and software, and direct rendering, which is the other case, was the fast hardware accelerated case. Let's see this one. So I'm recovering from that, so if I'm too incoherent because of being stuffed up, just let me know and I'll talk slower or not. All right, so as I mentioned, that's another mode of operation for the OpenGL binding. This is a direct mode, and in this case, that's a title slide. And so this is the overall picture. We have the application up and linking to the GL. And as I just explained, the indirect case is where the application talks to the Aiglx protocol module, which will then take the rendering request, put them in a network packet, send them over here to the X server, where the Aiglx module receives the request and decodes them, and send the rendering request into the GL core module. And this is a software rasterization I was talking about that takes the triangles, do the scanline conversion, and eventually copies the content to the stream. The other case is a direct case, and this is where we start to deviate from how the X server normally works. In this case, what we end up with is the driver actually being linked into the client. So we have the application up here, linking to the GL. But then, as we start rendering, there's a loader part that in the GL that starts out by talking to the X server. And it asks the X server if the X server can do direct rendering, because that's usually the preferred mode of operation. And if the X server says, yes, I can do that, it'll also pass back the name of the driver to load and the address of the frame buffer. So at this point, the client actually knows where in memory the frame buffer is, knows which driver to load, and it proceeds to load the dynamic. The driver is just a shared object, which it then GL opens and initializes with the address of the frame buffer, among other things. So at this point, we actually have the driver for the hardware is loaded into the client, and the client starts submitting rendering requests into the driver instead of filling all the network. So we receive the rendering request to the DRI driver, which instead of starting software rendering, will program the hardware to rasterize the trapezoids or the triangles as necessary, and it'll set up pointers to the textures where it's in the video memory, and it'll then render everything on screen directly. And the X server basically doesn't know what happened, because it just passed out the frame buffer address, and the driver goes up to do all the rendering. So that's the direct rendering case. And so since this is hardware, we load the driver on the client side that programs the hardware, and then the hardware does the rendering. This is also synchronous with fast rendering, accelerated rendering. And for a long time, indirect rendering was software, slow software. The external, I said the external doesn't know what happened, but it is part of the game somewhat, because you still need to respect the overlapping windows you have in X. So if you have an X window, you're running GLX and Tux Racer, and you drag another window on top of your Tux Racer window, the rendering has to respect that window. So you can't just render across your X terminal, whatever it is you're having on top of your Tux Racer window. So whenever the windows move or the clip regs change, there's synchronization going on between the direct rendering client and the X server. So the X server says, oops, you have to reread the clip list, and whenever the direct rendering client is ready to do some rendering, it goes and rereads the clip list so that it doesn't override the X server or other window. That was the indirect rendering. Okay, so accelerated indirect, which is what Aiglx is the case where we basically want the X server to load the hardware driver and use the hardware driver to implement the rendering requests as they come in. So we want to make the X server work the way it normally does for normal X requests, except we want to do it for 3D as well. But the reason why we have direct rendering in the first place is that we want performance. With the X server, with normal rendering, we don't really need that much performance, and the overhead for, we need performance of course, but the overhead for doing the marshalling and network access is negligible compared to the actual rendering, especially if you have to fall back to software. So when you see your X server being slow, if your scrolling is slow, if PDF document runs slowly, it's typically because we have to fall back to software and do some operations in software. It's not because we spend too much time sending network packets back and forth. It's always software fallback or something in that. But for OpenGL, we never do software fallback. It's always mostly always hardware, and since we're running Quake and we want the biggest possible frame rate per second, everything matters. So if we can avoid the network access here, we might get 1 or 2 extra frames per second in Quake, and then that's one of the reasons we direct rendering. So it is mostly performance. So the question is, we have direct rendering, which is faster than indirect rendering, and it does the same. Why would we want to accelerate indirect? And there's a few reasons. I'm listing GLX texture control, which is probably the primary driver that this work. So for Compiece, the compositing renderer, Compiece is an OpenGL application that renders the entire screen, the entire desktop using OpenGL, and it does so using the composite extension. What the composite extension allows you to do is you take the contents of a window, and normally when clients, the applications render to an X window, it's rendered directly into the frame buffer. You see the contents appear on screen as the application's rendered. What composite does is it takes all that rendering, and without the application knowing so, all the rendering now happens to an off-screen buffer. So the application will go and queue a number of rendering requests, and the X server will perform these rendering requests. But it won't actually appear on the screen as you usually did. It'll go into an off-screen buffer. This is why he needs all this video memory, because we need video memory for these off-screen buffers. But that's a different topic. It's pretty clever actually, because that allows us then to determine how are we gonna composite, how we're gonna combine these off-screen buffers on screen. And this is where stuff like transparent windows becomes possible, because we can do this in a second step. We can use extra channels in the pixmap to determine the transparency of each pixel, and if we can scale our windows as Compiece does, and Composite gives us all these possibilities, and Compiece actually implements it. But to go from the off-screen pixmaps to something company that we can use for rendering. We need some way to go from the pixmap in X server video memory, or at least X server memory, to a texture that we can use for rendering when we use OpenGL to render the desktop. And this is the texture from the drawable extension. It's called texture from pixmap now, so this is the extension. So that allows us to take an pixmap and use that as a texture. So as Keith mentions, when talking about moving the entire X server to HCL to OpenGL is probably not feasible because there might be deviations between different OpenGL implementations. But doing it this way, once we have OpenGL accelerated available inside the server, we can do this piecewise. It turns out that that's a really good way to accelerate, say, X video using OpenGL. We can do that for one driver where we have that feature available. It turns out we can do some of the compositing from random using OpenGL in a specific driver. We can enable that and use that. So it opens up a lot of this work inside the X server, and as such, it's an enabling technology. And of course, the ability to actually use accelerated OpenGL across a network is interesting in itself. If you have your 3D, you have an X server that has the possibility to load a 3D driver, you can actually have accelerated X on your desktop and run the application from an application server somewhere, so that you actually get accelerated 3D in this case. Of course, the caveat in this case is that if you have textures, you need to transfer. In this case, this is the drawback. You have to send the textures over the network. With direct rendering, you can download those textures directly because the client and driver is in the same cluster space. But all in all, accelerated iterate X is interesting because we can then accelerate these positive methods that everybody uses these days. So how do we do this? So from a 20,000 feet perspective, it's easy because we just need to let the X server load the DRI driver in pretty much the same way that the client would load the DRI driver. So, and a lot of the talk that the client does with the X server during the setup to startup phase. For example, the client asks the X server to support direct rendering ratio framework. There's a ping pong going on between the client and the X server during startup. All this is now just internal to the X server, so we can just call into a different part of the X server to say we use support direct rendering ratio framework. So all this takes place inside the X server now. There's no protocol going out on the wire. The X server already has the module infrastructure, so we can use DLO in the X server to load the DRI driver, link it in, and call into it. We need to provide some functionality to the DRI driver so that the DRI driver can call into the X server for various pieces of information. And in general, it isn't that big a task. It's just a matter of loading the driver and then tweaking the interfaces to make sure that the driver can get the information it needs to the X server and vice versa. Yeah, I'm going to skip this slide. This is about how we initialize the visuals. It's kind of messy, but it was messy before and it's still messy. So one of the more interesting case problems that we ran into doing this work was the DRI driver. So in a case where we have direct render, we have an application over here that loads the driver to program the hardware. So this driver will tell the hardware to go on the renders and triangles. At the same time, we have the X server over here to, say, move a window around by programming the hardware to copy one part of the screen to another. So both these applications are trying to access the same hardware and program it to do different things. So we need to synchronize this in some way. And the way to do this typically is to put a big old lock around the whole thing. So that's the DRI lock. The way it works is that the DRI driver knows that it has to synchronize access to the hardware. It knows that there might be different DRI drivers running. You can have two copies of the here, so you have Craig over here and Touch Racer here, and you can have several clients running at the same time, and you need to respect that. So the DRI driver that we load in the client to do the rendering already knows this, knows about the it takes it whenever it's about to submit command to render, and releases it once it's done. On the other hand, the X server doesn't know about the lock. It thinks that one without the X server, and the X server assumes that it just owns the hardware. But so most of the drivers are written to just render and expect whatever they submit to the card is still valid next time they come around and try to render. But that's not the case in this, because we might, from one, you submit a rendering request in the X server, maybe the X server gets swapped out and the direct rendering time runs, and it also keeps track of QX field, and then the X server swapped in again, and now the state is completely different from when the last time you touched the hardware. So we need some mechanism around this to make sure that the X server doesn't get confused. So what we do is, as soon as we receive a request from the socket, we take the DRI log and restore the state that the X server expects to see. And then we go off and render the request as usual. And then when we flush the pipe and we render all the requests that was sitting in our buffer, and just before we go back to sleep and wait for the next request, we release the log so that if the DRI driver will be able to acquire the log and do the rendering. So that's a ping pong between the X server and the client, the direct rendering client that is known to you, and it's not the most efficient way to do things, but it works. And so they ping pong the log back and forth. Yeah, as far, so the question is if this log issue is responsible for the freezing when you drag an application around, the application freezes, doesn't run until you let go of the window. And as far as I know, this is part of the problem. Because as you grab the window to drag it around, the X server is just saturated with requests to move the window around. It doesn't release the log while you move the window around. And the application is on the other hand, trying to render, but it sees that the log is taken all the time as you move the window around. So it just sits there and waits for the log to be released, which isn't released until you let go of the window and stop moving. So this it's not the most efficient way, because you get attacks like this where you stop rendering, but it basically works. And the better way to do this would be if the X server actually knew about the log and it could only take it for that short amount of time we actually need to do rendering. So if you submit an X request to copy a window from one part of the screen to another, or whatever it is the X server needs to do, then you would probably see this issue go away. Or if you could have a completely lockless architecture where you submit requests and the driver just renders it, but that's the different topic. But anyway, the interesting part is that with this lock setup, we get into a funny situation because we have a driver that, the DRI driver that tries to grab the lock before it does its 3D rendering, and now we're trying to run that from within the X server. So what happens is that the X server receives a request of the network saying, please render these 3D triangles. And then it goes and grabs it up, because that's what it does when it receives a request, and then calls into the DRI driver to render it. And then the DRI driver will think that I need to grab it up before it is rendered. But the X server already has it locked, so we have a recursive deadlock here. Because we're trying to run a driver that grabs the lock from inside the lock. So we have to do some hacking on this, and the simple way to do this is to just see if a request comes in, and it turns out that this is a 3D request. Then before calling into the driver to render the request, we just release the lock, go into the driver, and now the driver will say, oh, let me grab the lock and render this stuff, and that will succeed because we just let go of the lock. So the driver will be able to render whatever it renders, and then it will release the lock and return to the X-ray. And the X-ray will then immediately retake the lock in case we were about to do some 2D rendering. So the X-ray will take the lock, and eventually the X-ray will releases its lock and goes back to sleep. So this actually works fairly well. I mean, the whole taking and releasing of locks is not cheap because it's not just taking the lock, it's also about restoring the state of the graphics card to be what the X server or the 3D driver expects. But in the end, there's not much of a performance penalty to measure here, but there definitely it could be more efficient. Okay, so take that from normal. This is the big one of the big items for doing this, the big motivation. And the thing is, now that we have this 3D driver running from within the X server memory address space, we can say, all right, we've got the pixmap functions here, because the pixmap is an X server object. It lives in the X server address space, and now we have the 3D driver in the X server address space too. So we can say to the driver, all right, we've got this pixmap over here. This is your texture. So the implementing texture from pixmap is fairly simple now because we can just point to that pixmap. And there's a number of ways to do this. The best way would be if we have that pixmap sitting in video memory on the card. And typically that's what the X server will do. It will keep the video memory defined in a pixmap in an off-screen buffer in the video memory. And as you render your glyphs and fill the rectangles, whatever you do to the window, that drawing accumulates the off-screen buffer in video memory. And then when we want to texture, we want to render the polygon, the triangle, and want to use that pixmap as a texture, we can just point the 3D stack to that video memory area with the pixmap and use that as a texture. So that's the ideal case, but it doesn't work that way. I'll get into that later. I've got an illustration, but for now, what we're doing is we just ask the X server to not put the pixmaps into video memory, but keep the pixmaps in host memory. So whenever you do your rendering to a window, all this rendering is just rendered into host memory, in regular memory on your computer. And when we want to use it as a texture, we open GL stack to this host memory area, and the 3D stacks downloads the host memory and set up to texture. So we have this going back and forth from host memory to video memory all the time. Not back and forth. We go from host memory, copy it into video memory on every object. So that's what we're doing now. It's one of the biggest performance bottlenecks in the composite desktops as we've seen today, and it's something we like to fix. So the problem with, and as I said, we would like to be able to use the same in video memory. The same piece of video memory that the X server renders into, we'd like to be able to use that for texture without copying things around, but we can't do that right now because the way the X server manages memory is kind of awkward. So we have video memory, and what happens at start of this is that we take our memory for the frame buffer. So we set aside part of this video memory for the on-screen, the image that we see on screen. Then what happens is that if we have DRI name, we split the rest of that memory into two halves. And the X server manages one half of the video memory, and the 3D stack will manage another part of that we have two sections of the video memory. We can't really move objects around. The X doesn't understand the DRI memory. The DRI driver doesn't understand the X memory. So the problem is that if we render into the PixMap, this PixMap will live in the X video memory. And when we want to use it as a texture, we really need it to be in the 3D driver part of the video memory. But it's over that other half, so we can't do that. So what we'd like to do here is to just have one big view of memory on the card, and this is what the work that Keith mentioned, the Thompson guys are doing this work, doing a kernel level memory manager for the video memory, so that you can have your video memory, you can allocate an object in video memory, say, all right, this is a buffer, and the X server is going to render some stuff into it, thinking it's a PixMap. And then later on, you go as the DI driver, you use this buffer as a texture. And the DI driver will use that same buffer and the contents in there as a texture. So the work they're doing will allow this to work, and we can have zero copy text from PixMap, which will then get rid of the slow scrolling and the performance that we're seeing in compies and accelerated composite desktops. The other thing is that we have some regressions in functionality. So the way that direct rendering works is that as I said at the beginning of the talk, the direct rendering line will ask the X server for the address as a frame buffer, and then it loads the driver and renders straight into the frame buffer. But if we're running a composite desktop, it shouldn't be doing that. It should be rendering into that pixel which is aside for the window contents. But the direct rendering doesn't know about this and just renders into the front buffer as it's always done. And it doesn't work that well. So on the surface, it looks like it's working because this is Aiglx here is running in direct rendering mode. But when you try to move the window around, it's obvious that it's not working. So the window stays there. And then when the window settles down, the content moves. And the thing is that the compies doesn't actually update the X server's idea of where the window is until the window settles down. I mean, as long as it's wobbling like this, you can't really tell that the X server is this wobbly shape, so it doesn't even try. But the moment you let it go and it settles down and says, all right, I got a new position. It says, this is where it should be rendering. So it's only when it actually has a final position, it moves it around. Another thing is that it doesn't respect the clip lists here because sometimes we got a problem is I think that we have the window stacking is different because we have a big window sitting in front of the whole desktop. So none of these windows are visible anyway in the X services. Because there's a big window sitting in front of them. But companies does not render into this window, so we see the window anyway. But the DOI driver doesn't respect this and just renders into the framework. So that's something we need to fix. What we need to do here is again ties into the memory rendering work because we could tell the DOI driver to say when you ask for the framework address, we could in theory point it to a different address and say this is where it should be rendering, and then give it the address of the PixMap we wanted to render to. But there's a number of problems with that approach. So with the texture from PixMap idea, the way it's implemented now, we actually need to have this contents in host memory. But if we did it for direct rendering, it would end up in video. And so we couldn't easily use that video memory image as a texture. So that was it. Another thing is that even though when we look at the direct rendering window, again we see the one frame of data here, but there's actually several layers of data behind an OpenGL frame. And like OpenGL can do double buffering, in which case it will render to the back buffer. And then when you say swap, it will copy that comes from the back buffer into the front buffer. It also has depth buffers that tracks the depth of each pixel, so that if you render a new pixel in there, and that pixel is in front of that pixel that was there already, it'll cover it, but if the new pixel you're rendering turns out to be behind it, it'll just not update that pixel and keep the old value in place. It's got other types of buffers, stencil buffers, and there's a number of buffers, and all these buffers are allocated out of a big chunk of memory the same way that we allocate front buffers. So if you try to render into these buffers, they'll still clip the rendering according to the old level windows. And what we really want is we want a dedicated buffer for say the depth buffer and the double buffer. And that means that the 3D driver needs to know how to allocate a buffer. It doesn't know that right now. It just takes a chunk out of a big screen size buffer and then uses that. So with the memory manager work, the driver will be able to go and request a dedicated buffer for back buffer, for depth buffer, and it can then set up and we can render to an off-screen picture the same way we do it for regular memory. As mentioned, we have another problem, which is input redirection. And so if we in the expose case, this is when he didn't demo it, but I can show it. So I got two windows here, and this is my laptop. It's a 1024 by 768 screen, so there's not a lot of space. So I copy between two windows. I have to resize them and put them next to each other, or I can use the expose feature of companies, which will, if I throw the mouse pointer up into the corner, it'll scale it down like that. And I get a view of all the windows on my desktop. But the external doesn't know that the windows have been resized and moved around like this. The external still think that the three windows are more or less full screen size and all sit on top of each other. So if I could click into this window, the external will actually think that the mouse cursor is up here in the upper corner of the window, even though it looks like it's almost in the middle of the window. And if I want to select this text here, I would be clicking up here instead of what looks in the middle. So the point again is that the external doesn't know that the windows have been moved around and scaled like this. So it still tries to map input into the windows according to where it thinks the windows are. So in this case, Compass is clever enough about this because it doesn't try to let me drag an icon. Like what would be useful if you could drag this icon into this folder if I wanted to copy files around. So I click here and drag it down here. But Compass doesn't let me do that because it doesn't work. So what it instead does is that I can click on the window and select that window should be focused. Like this. And that's sort of the limit of what you can do. And what happens here is that companies is drawing the windows. So companies knows that the windows have been scaled down to the cloud. And companies can highlight the windows as I move over with the mouse. Like this. But I can't actually interact with the windows in this way. So, as Keith mentioned, the input redirection work that David has been doing actually lets the application instruct the external how to map input to windows. So if this window here is shown way up in the corner and scaled down, the compositing manager can inform X on this by sending it as a set of triangles that describe the relation between the window as it appears on screen and how it actually is in the external. So with that in place, we should be able to finally get composite working well, like how it was meant to be. So there's a few items left still, but it's getting there. Yep. Questions? That's a slide. support for transparent windows with OpenGL. So with regular X windows, we can request a visual, and the visual is just a data structure that describes how the pixels in a window is to be interpreted by the X server. With composite, it's not possible to say I want to ask for a visual that has an alpha channel, so that along with the red, green, and blue values for each pixel, you can also specify the transparency of the pixel. And you can use this to make clocks or windows like this that are shaped. And so what you can notice here how this part is fully opaque. You can't see anything through this. But in this case, this is slightly translucent. You can see the folder of the desktop behind it here. So you can do this for regular X applications, but if you want to use an OpenGL application and specify that you want a AADB vision for the OpenGL application, we don't currently support that. But I don't think it would be a big problem to implement this if the 3D driver can render an image that has the alpha values in it. So supporting this would be pretty easy because we just, once we have redirected direct rendering and the 3D driver can provide alpha values for each pixel, it should basically just work. So I don't see that as a big problem, but yeah. Yeah, XV is another regression that has been introduced with the composite because XV uses it's a different story, but the effects are similar. If you put an XV video on the desktop and you try to move it around, you see that the video doesn't play back correctly. And this is again that the XV extension uses a feature of the card that allows the card to do the color space conversion. And it uses a color key to indicate on the screen where it should be doing the video source and where it should be getting pixels from the frame buffer. And the thing is, as you wobble the window and move it around, the descriptions of you tell the hardware where to put the contents of the converted color space converted data. And this content can only be a rectangle. So you place the window on the screen, and as you move it around, you don't actually update that position in the hardware. And even if you could update, it would still wouldn't transform as the window does. So to get that working, we probably need to use OpenGL and use pixel shaders to do the color space conversion. I know Eric Anton has done some work in this area, and I think David has something in his XGL server as well that does this. But Aiglx is still not there, and that's something we need to work on as well.
What's being done about scrolling pixels, which was kind of slowish last time I checked?
Scrolling?
Scrolling like
in Firefox, anything, yeah. That's still slow, and that boils down to the way we do the texture from Pixar. The application does the external renders the window comes into host memory. So when you're scrolling in Firefox, normally what Firefox would do to scroll the window is it would ask the external to copy the area of 10 pixels however much you're scrolling, and then Firefox will render that script right now. But what we're doing now is the X server has been instructed to do this in host memory. So the scroll to scroll is not there. Now is a mem copy in host memory to copy the lines in place, and then it goes and renders all this stuff. And for text rendering, such as you want to copy the individual characters into the buffer, most cards are able to accelerate this compositing into the buffer. But in this case, we go back to software doing that too. So we have to composite the individual character and so forth. So this is slow, and once we've done that, we have to cover that entire buffer out to video image, to the texture, to render the new frame on the screen. So that's a big bottleneck right now. But hopefully, once the memory manager is in place, we can just render into one video memory buffer object. We'll be able to reuse that object in the user and the 3D stack, and we won't have to copy anything. We can accelerate or render. So that's the idea. It's still not there, but we know how to do it.
One last question. And what about window resizing?
Resizing. Yeah, that's a more involved issue. It really comes down to that some applications like to slow resizing, and that's the hard one to answer, because there's a lot more factors involved here. But we definitely need to do that. And some of the things that are interesting that we can do with composite is that we can actually synchronize the resizing between the application and the window renders. Before, there was no synchronization. You resize the window, and the application would get a number of resize events and try to keep up as best as it can. And you get these half-random windows. But now you can actually synchronize it, and you resize the window, and once the application has rendered a new frame, there's a composite window, you re-render it, and you get consistent resizing. But it's still something we see